Well, good morning and thanks for joining us. Today we want to talk about one of my favorite topics personally, and that's water potential. And we want to talk a little bit about, first of all, why water potential is important, but we need to get through the fundamentals first and try and help everybody understand what water potential is. And so in order to do that, we're going to talk about intensive and extensive variables, and then we're going to give water potential a formal definition. And then to further our understanding, we're going to talk about the different components that affect water potential, and then we can really get into the fun stuff. Then we can talk about water potential in the environment and why that is important and hopefully important for your research. And once we get there, we'll talk about water flow in the soil plant atmosphere continuum, talk about water potential in living organisms, and then we'll talk about water potential in soil. And that'll probably take up most of the time that we've got here. Before we get started with that, just wanted to talk about some of the history of water potential. Back in the early 1900s, the Bureau of Soils hired a few classically trained physicists, and one of those that they hired was Edgar Buckingham. And the reason that they hired these guys was to try and add a little bit of physics and understand the basic science of soil science. And so they actually brought Buckingham in to look at gas flow in soil, but he ended up getting a little sidetracked looking at unsaturated water flow in soil. And he realized pretty early on that water content didn't drive water flow in soil, and that something that he termed capillary conductivity did. Turns out that Buckingham's background in physics with the electronics and understanding Ohm's law and then also applying Fourier's law really helped him understand the water flow in soil, and he didn't call it water potential, but as it turns out he was really discovering that water potential was the factor that drove water flow in soil, and that's one of the fundamental things that we will talk about today. Let's now talk about extensive and intensive variables. To really understand the state of matter or energy in the environment, you need to understand two types of variables. One of those is the extensive variable, and the extensive variable really just tells you the extent or amount of matter or energy in the environment. And in terms of water, it tells you the extent or the amount of water in soil or plant tissue, and that of course is water content, is the extensive variable. The intensive variable describes the intensity or quality of that matter or energy, and in the case of water, it's the water potential that describes the intensity or quality. And if you look at the slide here, you'll see that in terms of heat, the extensive variable is the heat content, okay, just the total number of joules of energy that are contained in some object. The intensive variable is the temperature, okay. In terms of electricity, the electrical charge is your extensive variable and the voltage is the intensive variable. Now, what we care about is water in the environment, and the extensive variable is the water content, which simply tells you the amount of water in the soil or in some plant tissue, whereas the water potential tells you the quality of that water or the energy state of that water, or how tightly bound that water is and how available that water is. And there are several reasons that the intensive variable is often the more appropriate variable to understand. It'd be best to understand both, but often the intensive variable tells you more. So here's an example in terms of heat. Okay, so on the right you have a piece of very hot metal. Okay, temperature is very high, but it's relatively small, so it doesn't actually contain a lot of heat. On the left, you see the hull of a large cruise ship that, because it's driving around through water with icebergs, you know it's at a low temperature, but it's very large, so it contains a lot of heat. It contains, in fact, more energy than that little hot piece of metal. Okay, so in terms of the extensive variable, the hull of that ship contains more heat than the hot piece of metal. In terms of the intensive variable, the hot piece of metal is at a higher temperature. Okay, so I think we all fundamentally understand that if you placed those two in contact with each other, well, which way would the energy flow? Well, I think we all know that the energy would flow from the high temperature to the low temperature, okay? It flows along the gradient of the intensive variable, okay? The same is true in soil or in plants. So now let's take this extensive versus intensive variable and apply it to soil. So you can see on the left that we have a clay soil, on the right we have a sandy soil. To the clay soil we've added here 25% water by volume to achieve 25% volumetric water content. In the sandy soil we've added 10% water by volume to get 10% volumetric water content, and then we've measured the water potential on both of those with a tensiometer and a dew point hygrometer. So now what do we end up with? Here we have 25% water content in the clay, 10% water content in the sand. The sand has a water potential of negative 25 kilopascals, whereas the clay has a water potential of negative 1300 kilopascals. And I know that we haven't really talked about the units or the fact that these are negative numbers, but the question I want to ask is, if you put these two soils into contact with each other in the state that we've described here, which way is the water going to flow? Is it going to flow from high water content to low water content? Or is it going to flow from high water potential, not very negative, to low water potential, a very negative water potential? Well, I'll give you a cheat here, and this is one of the most important take-home points that I want to get across today, is that the second law of thermodynamics tells us that water will always flow from high potential to low potential, okay? The intensive variable temperature says that energy will always flow from that high energy state to the low energy state. In terms of chemical potential, it's the same. Things flow from high chemical potential to low potential. So water will always flow from high potential to low potential. And a point that I want to make here is that if you leave natural systems, or if you leave systems and let them come to equilibrium, the water potentials will equalize. They will come into equilibrium. Because of course they're flowing from high potential to low potential, and they'll do that until the potentials equalize. So now getting back to our question, okay, is if you put these two soils together, will the water flow with the water content gradient or the water potential gradient? Well, I think we know after that last slide intuitively now that the water will flow from high water potential to low water potential, always. Okay, water content does not govern the flow of water in the natural environment. Water potential gradient does, and that's one of the things that's pretty important for us to understand going forward. So let's give a formal definition to water potential now. Water potential is the energy required per unit of water to transport some small amount of that water from the sample to a reference pool of pure free water. So basically, if you took a soil sample or a plant sample and you pulled some water from that sample out to a pool of pure free water, the energy that it requires for you to pull that water out, that is the water potential, okay, of the water in that sample. Maybe a more intuitive way to think about this is that the water potential describes how tightly that water is bound in the soil or plant sample. So the more tightly that water is bound, the lower the water potential, because you have to add more energy to get that water out. Some important points that we need to understand about water potential. First of all, it is a differential property. That means we have to specify a reference and compare the other water to that reference. So the reference that we specify is pure, free water at the soil surface. And we define that pool of pure, free water at the soil surface as having 0 water potential. All the water we have in the environment that is bound or diluted by solutes has a water potential of less than 0. It's a negative water potential because you have to add energy to get that water out to overcome the binding and get it back to your pool of pure free water. And so that's one of the points that I have there, is that water in animal tissue or plant tissue or soil is very different from water in a glass. It's bound to the surfaces, it's diluted by solutes, it's under pressure or tension, and it's at a very different energy state than free water at zero potential. And so we have a lot of names for this. Water tension, soil suction is a popular one in geotechnical engineering. Pore water pressure and negative pore water pressure is the same thing as a water potential. Those are all names that are used to describe the same quantity. I think generally in soil science and often in ecology we would refer to that as water potential. And we typically use units of pressure. Megapascals and kilopascals are pretty common. Bars is still pretty common. That's kind of old school. And we also use lengths of water, meters or centimeters or millimeters of water as a pressure unit. The real units of water potential are energy per unit mass or energy per unit volume. So joules per kilogram is the real unit, but if you take into account the density of water, then joules per kilogram becomes kilopascals. So it's easier for us to just use units of pressure. So what are the different factors that influence the water potential in the natural environment? Well, we have 4 that we have to account for. The first of those is the binding of that water to a surface. The second is the position of that water in a gravitational field. So basically the vertical position in relation to our reference, which is the soil surface typically. Also, if you add any solutes to the water, that lowers the water potential. And finally, if you exert a physical pressure or a physical tension on the water, that also affects the water potential. And the total water potential, you see here as psi sub t, is simply the sum of all 4 of those different components of water potential. So total potential is just the matric potential, okay, that's the adsorption to different surfaces, plus the gravitational potential, which has to do with the position in the gravitational field, plus your osmotic potential, which has to do with the dilution from solutes, and then your pressure potential, which is the hydrostatic or pneumatic pressure or tension that's being applied to that water. So the total is just the sum of the components. That's pretty nice and handy. So let's talk about each of those individual components in a little bit more detail. First, let's talk about the matric potential. The matric potential arises because water is attracted to most surfaces via van der Waals forces and hydrogen bonding. So the picture at the top right that you see, I had my technician take that this morning. That was just a droplet of water that was placed on a piece of plastic, and then you turn the plastic over, and what happened? Did the droplet fall off? Well, no, the droplet's stuck there. Why? Well, it's attracted to those surfaces. It's hydrogen bound to that surface, and so that water droplet is no longer at zero potential now. Now it has a negative water potential because those matric forces have lowered its water potential, and you would have to use some energy to remove that water from the surface and take it to a pool of pure free water. So this matric potential, first of all, is always negative, okay? And another important point is that in soil, the matric potential is generally by far the most important component of the water potential. You can have a significant osmotic potential if you have salt-affected soils, but by and large the matric potential is the one that binds the water in the soil. And why is that? Well, that is because soil, of course, is made of lots of small particles, and there's a huge surface area there, and so there's lots of surface area for the water to bind to. You do see this in plants. The picture on the right is a bunch of plant cells, and then the intercellular spaces have water in them, and there is a matric potential that binds that water to those cell surfaces, but you generally would see it more like the picture in the left, which is soil with some large particles and then some small particles. And the binding of that water to the soil is highly dependent on the size of the particles. So in a sandy soil, okay, let's look here, and we have 2 different soils now with the same water content. Okay, we have a sandy soil here with a water content of 0.1 meters cubed per meter cubed, or 10% water content. Okay, if you look at the moisture retention curve, these are 3 moisture retention curves, moisture release curves, soil moisture characteristic curves. Those are all the same name for the relationship between water content and water potential. Okay, each soil has its own relationship, but I want to use some generic soil water retention curves here to understand the effect of surface area. So a sand has relatively large particles, and so it has a relatively small surface area. So at 10% water content, this sand has a very high water potential. Okay, it's up maybe only negative 25 kilopascals. The water is readily available. Now if you take a loam soil that has some clay particles in it and a much larger surface area, okay, the loam soil will have a lot of small particles and a bigger surface area, then at the same water content, that soil will have a much lower matric potential, meaning that the water is bound much more tightly because there is so much more surface area for that water to absorb to. So in this case, that loamy soil at 10% water content may have a matric potential of negative 1500 kilopascals, which is getting pretty low. Okay? Okay, our next component, gravitational potential. Gravitational potential, again, is just due to the difference in height of a sample between the reference height and the height of the actual water. So in this case, we've defined our reference level as the pool at the bottom of this waterfall. This is a 10-meter waterfall, so it's pretty easy to calculate the potential energy there. It's just gravitational acceleration multiplied by the distance, and that translates into a gravitational potential of positive 98 kilopascals. Now, you notice that matric potential can only be negative. You can only go from 0 down, but in fact, with a gravitational potential, you can have a positive potential or a negative potential depending on where you are in relation to your reference. Okay? And so here's the opposite case where our reference level is at the soil surface, and now we have water that's a meter deep. Okay, the gravitational potential on that water is 9.81 meters per second squared times 1 meter equals negative 9.81 kilopascals. So, surface water, okay, streams and rivers flow downhill, of course, because of the gradient in water potential, and in this case it's a gravitational potential that causes them to flow downhill because they're at a higher potential if they're higher in the gravitational field and at a lower potential if they're lower, so water always flows from high potential to low potential, and so that's why you get surface water flow. Osmotic potential, this is our third component. Osmotic potential arises from the dilution of water and the binding of water by the solutes that are dissolved in them. This again is always a negative potential. There is no positive osmotic potential. But this only affects the system if there's a semi-permeable barrier that's present that allows water to pass but doesn't allow the solutes to pass through. And so you might say, oh, you really only see this in a chemistry lab with some osmotic barrier, but that's not true. This is quite common in nature. Some examples are plant roots. Plant roots will allow water to pass quite freely but block most of the solutes, and so then you have your semi-permeable barrier, and so if you're dealing with plants, you do have to understand and take into account the osmotic potential. Another place that this is important is in the cell membranes of plants and animals. And finally, one that's a little bit less intuitive is the air-water interface. So if you have water that's in contact with the air, the water can pass through that interface in its vapor phase, but the salts stay behind. So if you're measuring the total water potential, you have to account for the osmotic potential with that air-water interface as well. Okay. Osmotic potential is pretty easy to calculate. You can calculate that if you know the concentration of your solute, okay, in moles per kilogram, then you multiply that by your osmotic coefficient, which just depends on the type of solute it is, on individual solutes, but generally is between 0.9 and 1. Then if you know the number of ions per mole, so for sodium chloride you have a sodium and a chloride, so 2. For calcium chloride you have a calcium and 2 chlorides, so that number is 3. And then multiplied by the gas constant and the Kelvin temperature, then you get your osmotic coefficient quite easily and quite simply. Okay, our last component, our pressure potential. This is the one that arises from what we think of as pressure or vacuum or suction. Okay, hydrostatic or pneumatic pressure being applied or being pulled on that water. So there are several cases of this in the natural environment. Certainly surface water bodies can have a positive pressure. If you swim down below the surface of the ocean or a lake, you can actually feel the pressure being exerted on you. That is just a positive water potential. Okay, same is true in groundwater. If you go below the vadose zone and get down into the groundwater and go a little deeper, then you have a pressure head or a positive pressure potential being applied. You also see this in plants. You see this in leaf cells, in that you see turgor pressure. So the picture on the right has a flaccid leaf on the left and a turgid leaf on the right. And the turgor pressure is just a positive pressure potential, positive water potential that is causing that leaf and that plant to stand up. And we'll talk more about that in a little bit. Also, blood pressure in animals is a positive pressure potential. You also see some cases of negative pressure potential in the environment. So in the xylem of a plant, as the water is pulled up from the soil through the roots, through the xylem, and up into the leaves, there is a negative pressure potential in the xylem, which causes water to flow up through the plant. Okay, so now those are the four components, and we've talked a little about those. Hopefully, if we go through a few examples, these things will start to make a little bit more sense. So let's take the case of some pure, free water in a glass. And we've defined our reference height up here as the height of the water. So by definition, the water potential of pure, free water at the reference height is 0. So our total potential here is 0. Matric potential, we're going to call it 0. It may not be exactly 0 because you might see some residual bonding, from around the glass, but we're going to say for the case of argument that's 0. Gravitational potential is 0 because we're at the reference height. Osmotic potential, we said it's pure water, so that's also 0. And our pressure potential here is also 0. We're not below that water surface. Okay, but now what happens if we go 10 centimeters deep in that glass? What's our total water potential here? Well, we said that this is an equilibrium example. It says up there in the title. So if everything's in equilibrium, what does that mean? Well, we said water potentials want to equalize if they come into equilibrium. If they're in equilibrium, then the total potential is equal. So if our water potential here was 0, or water potential anywhere in this system is 0. Okay, so our total water potential is 0. Matric potential still 0. What about a gravitational potential? Aha, okay, so now we've come 10 centimeters deep, and so we have a negative 10 centimeter pressure potential, which is about negative 1 kilopascal. Osmotic potential is still 0, but now our pressure potential, okay, because we're 10 centimeters deep, this water is exerting pressure on the water down here, and so we have a positive 10 centimeter or positive 1 kilopascal pressure potential. Okay, so the sum of all these need to equal 0, and they do. We've got a negative 10 centimeter gravitational and a plus 10 centimeter pressure potential. Okay, what happens if we suck the water up a little ways into the straw? Now we have pulled the water up 5 centimeters into the straw. Again, our total potential is 0. Okay, we're still in equilibrium with this reference height. Matric potential is 0. Gravitational potential now is plus 5 centimeters. Okay, we've pulled this up 5 centimeters, so we're half a kilopascal of positive gravitational potential. Osmotic still 0, but now we have a negative pressure potential. The fact of pulling a suction on this has pulled negative 5 centimeters or negative half a kilopascal of pressure potential. So now again, our gravitational and pressure potentials basically sum up to 0 once again. Okay, another example. This one's slightly different. In this case, there is no suction on this. This is a capillary tube, and the water has spontaneously climbed up through this tube due to our capillary forces or our matric potential. So in this case, our total potential is still 0. Okay, maybe it wouldn't be because we added some food color to here. We'd have some osmotic potential, but we'll neglect that. Okay, so here's our reference level. What's our matric potential? Well, if this is climbed 3 centimeters up, then we have a negative 3 centimeter matric potential, okay, or negative 0.3 kilopascals. And that's balanced by the gravitational potential. Now we have a gravitational potential here that's exerting 3 centimeters of gravitational potential on that water, and so again these balance, but now it's not a pressure potential that's pulling this up, it's a matric potential that's causing that water to climb. Okay, one last example, and this one's quite a bit more interesting than those other examples, I think, because this one's from the real environment. So let's say we, well, first of all, this is a leaf, okay? These are cells inside the leaf. Vacuole inside the cell has some sap in it, okay? And then this is water that resides outside the leaf cells, but inside the leaf, some intercellular water. And we have used a pressure bomb or a dew point hygrometer to measure the water potential, the total water potential of this leaf at negative 700 kilopascals, and that might be a typical value. It certainly would be a value that wouldn't surprise anybody for a leaf water potential. Okay, so if this is in equilibrium, this leaf is in equilibrium, or if it's in steady state, then what do we know about the total water potential inside the cell? Okay, well, we know it's in equilibrium, so we know that the total water potential inside the cell is the same as the total water potential inside the leaf, negative 700 kilopascals. But we maybe have used, maybe we've gotten a sample of this cell sap, and we've measured its osmotic potential at negative 1500 kilopascals. So it has a very significant osmotic potential. It's very salty. This is something that plants do. Well, we'll talk about why in a second. So what is the water potential that's balancing this out? We know that it's going to come into equilibrium. We know that the total potential in the cell is 700 kilopascals. Osmotic potential is negative 1500. Well, we have to have some positive pressure potential there to balance those out. And so negative 700 kilopascals equals negative 1500. That's the osmotic potential plus the pressure potential. And so we know that the pressure potential inside that cell, the turgor pressure, is positive 800 kilopascals. Okay, this is why plants stand erect. This is why leaves, unless they're under water stress, are not wilted, why they're turgid, is because the water will be pulled into the leaf until the pressure potential balances this very negative osmotic potential and causes the total water potential here to be the same as the total water potential here. Now, what happens if you have water-stressed conditions and you have transpiration going on and the water potential in the leaf begins to fall, begins to go more negative? Well, the water potentials are going to balance themselves, so water will flow out of the cell into the intercellular spaces until, again, the total water potential here is the same as the total water potential here. Well, as that water flows out, the pressure potential decreases and the plant wilts. And so the wilting of plants is simply a manifestation of the pressure potential in the leaf cells. So I think that's a pretty interesting example of water potentials that hopefully helps you understand these different components and how they interact. Now, before we move on to talking about some more water potentials in the environment, I need to touch on the fact that water potential and relative humidity are related by the Kelvin equation. This comes from thermodynamics, but what it shows us is that if you know the relative humidity of a sample and you know the temperature, then you know its water potential. This is simply the gas constant, and this is the molecular mass of water. So these are constants. If you know temperature and humidity, you know the water potential, and vice versa. If you know the water potential and temperature, you know the relative humidity. And that will become more important in the Water Potential 201 seminar, virtual seminar next month, when we start talking about measuring water potential, which also is near and dear to my heart, but I think you'll be talking with Colin on that one. So what are the ranges and units of water potential that we typically would see in the environment? Well, we said that pure free water is 0 water potential, and that also has a relative humidity of 1 or 100%. Now, if you're in saturated soil, okay, then by definition you would have no matric potential there because you're saturated, and so the water potential would be zero unless you had a very large osmotic potential in that soil, if you had a salt-affected soil. But saturated soil is very close to zero water potential. Field capacity is the point at which gravity no longer drains appreciable amounts of water from the soil, and this would be a very moist soil, and this, in the United States, we call it negative 33 kilopascals. In Europe they call it about negative 10, but regardless, this is a value for pretty darn moist soil. Permanent wilting point is the point at which plants basically cannot access water from the soil anymore. If you bring the soil down to this water potential, to negative 1500 kilopascals, then in theory the plant, even if you added more water to the soil, would not recover. So it's basically when it's lights out for the plant. And so these two levels kind of define the range of water availability for the plant. Air dry is negative 100,000 kilopascals. Now, of course, that depends on relative humidity, so we're just saying that air dry is a humidity of about 50%. And then oven dry is about negative 1 million kilopascals, which is a very low relative humidity. So this encompasses about the full range of water potentials that you would experience unless you went to some really extreme steps. Okay, so now we've talked about some of the fundamentals. Let's switch gears a little bit and talk some about water potential in the environment. And first thing I want to talk about is water flow in the soil-plant atmosphere continuum. And by soil-plant atmosphere continuum, I mean the water continuum, or the water interconnectivity between the soil, the water in the soil, going up through the roots, through the xylem, into the leaves, and then out into the atmosphere. And so the flow of water through that continuum, from the soil, through the plant, and into the atmosphere, is strictly a function of the water potential gradient. We know that water always flows from high potential to low potential, so your water potentials in the soil will be relatively high. This is negative 300 kilopascals, is a middle of the road soil, a little bit dry, but look at that in comparison to in the outside air of negative 100,000 kilopascals. Okay, so obviously the water will try and flow from this high potential to this low potential. And this is true not only in plants. Water flows from high potential to low potential in soils. That's the driving force that Edgar Buckingham put his finger on back in the early 1900s, that it's the water potential gradient that drives all water flow. Water potential also defines the availability of water for biotic processes. Okay? If you're told the water content of something, you have absolutely no idea if bacteria can exist, if fungus can propagate, if plants are going to do well in that. But if I tell you the water potential, then you know exactly if that water is available for these biotic processes. So for instance, in food, this is a big part of what Decagon does, the other half of our company, but pathogenic bacteria cannot propagate at lower than negative 19,000 kilopascals. So this is staph A. This is a picture of staph A, that pathogenic bacteria, if you're below negative 19,000 kilopascals, then they're not going to propagate and your food's going to be pretty safe. Mold can't grow below about negative 50,000 kilopascals. Okay, so you wouldn't see any mold growth. Also, dormancy in organisms, plants, and microbes the dormancy levels are defined by the water potential, not by the water content. And finally, seed germination. Seeds begin to germinate once the soil or whatever their environment is wets up past a certain water potential level, not a certain water content level. So you'll see there that just a general range might be negative 2,000 kilopascals is when seeds might begin to germinate. So while we're talking about plants, let's talk a little bit about water potentials in plants. We talked already about the osmotic potential inside the cells of plants. Well, so the plants actually actively pull solutes into the cell to establish a low osmotic potential, at least in part, so that they build up the turgor pressure and hold the leaves at angles that are optimal for intercepting sunlight. And those osmotic potentials generally range between -1,000 and 2,000 kilopascals. Plants, if they're experiencing water stress, can actually adjust that osmotic potential and bring that lower to try and maintain turgor pressure, even though the leaf water potential is lower than what's, I guess, comfortable for them. So then let's talk about total leaf water potential. At night, when the plant stomata close, the total leaf water potential will equilibrate pretty well with the soil water potential that the plant is experiencing. So in a moist soil, if you do pre-dawn water potential measurements, then you might get measurements that are pretty close to zero. And those pre-dawn leaf water potential measurements are a pretty good indicator of the integrated water availability in the soil. And you can see some poor grad student here taking pre-dawn water potential measurements. Pretty common measurement to make in ecophysiology, and it's just not really that fun. And here's an example of somebody using liquid nitrogen to explode the leaf cells to express the sap and then measure the osmotic potential, probably with a thermocouple psychrometer or dew point hygrometer. But getting ahead of myself, that's in 201. Okay, next month you get to talk about the measurements. So we said that the leaf water potential at night comes to often a very high level if there's high water potentials in the soil. But during transpiration, the leaf water potential can be lowered dramatically. If there are limiting conditions, if the soil water is limiting, then the leaf water potential can drop almost all the way to the osmotic potential in the cell. Now, of course, the leaves would be wilted and drooping at this point, but that's pretty common to see. So, in fact, the leaf water potential can range from around zero all the way down to about -2,500 kilopascals in a single diurnal cycle. Okay, sometimes this happens every day with plants, and that's an extreme example, but it's certainly possible and it does happen. But if you take your leaf water potential measurements when you've had transpiration for a good long time, so midday leaf water potential measurements, those can be a really good indicator of plant water stress. However, you have to be careful that those are pretty highly dependent on the transpiration rate, and so you have to factor in some other environmental parameters to make those directly transferable. And so you'll see here a couple of instruments. This is a pressure chamber for making leaf water potential measurements, either pre-dawns or midday, and you can also make those leaf water potential measurements with the dew point instruments. There's a growing body of work that's showing that the water potential in the xylem of plants may actually be a better indicator of plant water stress or plant water status. It's a little bit more stable than leaf water potential, but it's also more difficult to measure. I think there's some companies that are now making stem psychrometers that can measure the xylem water potential, and I know there's research being done with small tensiometers that you could actually insert into the xylem and get a measurement of xylem water potential. But those are difficult measurements, and I don't think that's a terribly common measurement at this point, although it may be in the future. So now let's shift gears a little bit and talk about water potential in the soil. The soil water potential really defines the availability of water for a plant, or microbes or whatever else, but I think most of us care more about plants. One of the beautiful things about water potential is that number is directly transferable from one soil type to another. So if I tell you that I have, 20% water content, can you tell me if the plants are water stressed in that soil? Well, not without more information. If you're at 20% water content in a sand, then they have plenty of water and the water's draining straight through. If they're at 20% water content in a clay soil, then those plants are probably severely stressed. But if I tell you that you have a water potential of -50 kilopascals, then it doesn't matter what soil you're dealing with. Okay? -50 kilopascals is the same as -50 kilopascals anywhere else. And so that's one of the beautiful things about water potential, and that's one of the things that makes water potential a better measure than water content if you're dealing with plants and if you're dealing with biotic systems. You'll still see in the literature, you know, people saying, oh, and we measured this parameter and the soil water content was 15%. Well, what does that really mean? It doesn't really mean anything unless you're dealing with water balance, okay? If you're trying to understand the amount of water in a soil, then of course water content is what you want to measure. But if you're trying to deal with living systems, then water potential is a better measurement. And here again we have field capacity. Field capacity is actually defined as the water content that is achieved after a soil, you know, is thoroughly wet and then allowed to drain for a day or two. But that generally corresponds to something between -10 and -33 kilopascals. And this is really the upper limit of plant available water, because any more water than that or any higher water potential, and the water is just going to drain through the soil and be lost to the plant anyway. The opposite end of that is your permanent wilting point that we talked about, and this is really the lower limit of plant available water, -1500 kilopascals. But note that this is really kind of a cutoff point where plants are dying. Plants begin to stress and begin to lose yield at much higher soil water potentials. And this is pretty important for especially irrigation management. This is one of the things that I wanted to touch on, that there is a large body of agronomic research that has pinpointed exactly what water potential causes plants to start losing yield. So you can see on the right side over here, there's a whole list, you know, a whole table of different plants and what water potential you would want to maintain the water potential above that to keep those plants from losing yield, okay? And again, these water potential levels are valid for any soil, basically. So if you're growing lettuce, you want to keep your water potentials, you know, above about -50 kilopascals. If you're in a sand, if you're in a loam, if you're in a clay. Again, you could not do this with water content. You see irrigation studies that say, oh, the water content was, you know, 20% water content. Well, it doesn't really tell you much. It does tell you how much water you need to put on to replenish back to that level, but it doesn't tell you much about if the plant was stressed at that level. Now, on the flip side, a lot of people now, a lot of growers are now using deficit irrigation in perennial crops. And by deficit irrigation, what you do is you hold the soil at a lower water potential to intentionally induce drought stress on the plant. And this really serves to do two things. It minimizes vegetative growth. Okay, you have less pruning to do, and maximizes the sugar production in fruit, which gives you better flavor. And so this is pretty common in fruit trees, and especially common in wine grapes. You get your best quality wine grapes if you hold the water potential in the soil and the water potential, therefore, in the plant at a stressed level. And those stress levels are transferable again from one soil to another, whereas the water content, again, really doesn't mean very much. So now I put this last one in to try and help us understand. I guess I've maybe belabored this point a little bit, but here we have, we're talking about water availability in different soils, and here we're talking about a loam soil versus a clay soil. So if I told you I have a soil with 26% volumetric water content, could you tell me if plants are going to grow in that, or if they're going to be stressed? And the answer is no, because in this loamy soil, if you have 26% water content, you have a water potential that's up above field capacity and you're losing water. It's a muddy soil and water's draining right out. But if you're in a clay soil at 26% water content, here you have something really negative, like negative 800 or 900 kilopascals, which would be quite stressing for the plant. So this just is the final thought that water content can tell you some things, but water potential will generally tell you quite a bit more. And so that leads me into the take-home points. We're running out of time here a little bit, so I want to sum up what we've talked about. first thing I'd like you to take home and make sure you understand is that water potential describes the energy state of water in the environment. It's our intensive variable, and it's really useful for a lot of things. Biggest take-home point is that water in the environment will always flow from high potential to low potential. That water content won't tell you that, only the water potential will tell you that. And then the final take-home is that water potential defines the availability of water for organisms, for biotic processes. It defines the availability of water for plants, defines the availability of water for microbes, for fungus, for all living things. And so that's one of the main things that makes water potential very important. So that's all we've got for the Water Potential 101 virtual seminar. Thanks for joining in. We'll take some questions now, and I'm sure there's going to be some, because this is a pretty complex topic and pretty challenging to try and get through this and do a good job of teaching some of this in 45 minutes. I'd like to encourage you to tune in next month for Dr. Colin Campbell's virtual seminar, his Water Potential 201, where we'll get into another topic that's near and dear to my heart, and that's measuring water potential. Thank you.